Alright, hell yeah. So we're going to do a moment of inertia problem. This is out of the Schwamm's book, Engineering Mechanics Dynamics. So hell yeah. So we have a square that has some sort of just linear velocity. It hits a bump, and then it has a completely inelastic collision. So no forces are applied to the object, and then it just starts to rotate. So it just perfectly hinges right there. And then we have conservation of angular momentum. And I think we've all heard that, conservation of angular momentum. At the end of this, I want to know if conservation of linear momentum, if I can use the same strategy, and I don't think I can for this problem, and I don't know why. So, you know what I mean? But this is where angular momentum is just too confusing. You have i's and omegas. You know, angular velocity, omega, we can handle that. But this I, this is mass moment of inertia. This is second. It's the second mass moment of inertia. And what the hell is a, you know, anytime you see I, it's a moment of inertia, you know what I mean? And for angular conservation of angular momentum, it's a mass moment of inertia. So just real briefly, I'm going to draw a wrench, and then we have a handle and we apply a force. Cool, and we get this. The torque on this is the force times distance. Well, guess what? The moment on this is force times distance. And this is what they call a first moment. You know what I mean? Who knew? Who knew a force times a distance was a first moment you know, I don't even know what you call it. You know, I think first moment of force. You know what I mean? Because if you have an I-beam, you know what I mean? Typically what you do is you like, hey, find this area, and then you'll go area distance squared. Well, guess what? That is the second moment of area, because you did the distance squared. If we just took some sort of parameter that was just a times distance and we thought that was useful, well, cool. This is the first moment of area. You know what I mean? So there you go. And when we have you know what I mean, like a hoop of metal, and we have some sort of mass, you know what I mean? We've got a bunch of them, but we're just going to call that, you know, a mass right there. We can say the second moment of area. It's the mass moment of inertia, but it's the second. Well, what do we call this one? We call this one the second moment of area. So this is going to be the second moment of mass. So whatever the distance is, and in this case it's r, we're going to take, well, hell yeah, we're going to take that mass and then the distance squared. So it's very similar to md squared, and there you go. So that's in a nutshell what the hell the first moment and the second moment. Who knew? Who knew? It was just kind of spelled out. But the fact that they don't call it the second moment of mass, they call it the they just call it, and so it's either the second moment of mass, or it's the mass moment of inertia, or it's just the moment of inertia. If people are talking about moment of inertia, it's just like, well, in material mechanics, they're talking about this, the second moment of area. But if you're talking about anything that's moving, you probably are talking about the mass moment of inertia. Okay, hell yeah. So now, I don't want to make a too long of a video, so we're just going to go in to how to do this problem in a very simplistic way. Alright, hell yeah. So, this problem's interesting. Well, so one way that I wanted to solve, and we'll get to the end, I just figured, you know what I mean, the linear momentum initial is equal to the linear momentum final, you know what I mean? This happens when you have two pool balls that hit together, collide. That's going to happen. But you know what I mean? I'll have to answer my own question in the end, because if I set that up, that I say, hey, this linear mass times velocity, this is 9 kilograms, and we have 4 meters per second. What I want to equivocate that with is I want to cut this up into 4 chunks of mass, and the second it hits, it's all angular velocity. And then so each of these individual chunks of mass basically have a tangential velocity tangential, and that's to something normal. So what I use is like, hey, that's radians, times radius. And in this case, we have radians per second times radius is going to be the tangential velocity. Well, it seems like conservation of linear momentum would just be like, well, look at that thing. It's technically going in a straight line that way, just for a small little snippet of time. And so why isn't this velocity, WR, times this mass, which is the 9 divided by 4, and then do the same thing here, you know what I mean? And we have some sort of radius from this point of rotation. But for whatever reason, I don't know why this is not true, and that's what I want to learn. So that's kind of cool when you pick up a subject. You're just like, okay, we have this concept that angular momentum is conserved, but I'm sure there's cases where linear momentum might not be. I just don't know how to solve my own problem on that one. But when it comes to angular momentum, what we do is you have to take some sort of like cross product. You know what I mean? You have to pick a point, and then we have to say, hey, look at this. When this mass in comes, it's going on a straight line like this. And so we take the center of that mass, and then we have a radius, and then we take a cross product between the radius times the linear momentum. Kind of what we all know is just mass times velocity. Now it will be a cross product of the vector. You know what I mean? So it's essentially doing that same thing that so when you do the cross product, well, the velocity is just in this direction. You know what I mean? And then so it's only going to be the component of this radius in what direction? Probably this. No, it's the cross product. So it's gonna be perpendicular. So this distance right there. So that distance right there. So we have and they're saying that this distance is S. I don't like that. Well, let's change it to A. You know what I mean? I think A is typically used for a square. If you got a square, it's got side A. So everywhere where it says up S in here, just use A. And so hell yeah. So we have a distance of A divided by 2. And since we did kind of the cross product, or we kind of figured that out, we're just going to have the mass of this, which is 9 kilograms, times its velocity. And that's going to be 1.5. Cool. So that's all they did right there. You know what I mean? And now we're going to say, and this is the equation. This is why this is the conservation of angular momentum. But we don't want to use I's. We want to figure out what the hell the I means. So this is what we're going to do. So now we're going to, and see how this was hey, we picked a mass, we said it had a velocity, and then it was some distance away from this origin. But the cross product was important. We had to take only the component that was, see how this velocity would be going this way before it hits? Well, we can only take that distance. So so if we wanted to do the additive approach to get this, we could still cut it up into 4 chunks. Each of these chunks has a velocity that way. And then we could say, we would still have to do the cross product to each of those. But because this velocity is only that way, the cross product says, hey, the distance has to be 90. Just like that wrench that we were showing a moment earlier right here. You can't torque a wrench, by putting a force that way. So any component of the force that's in the vertical direction is useless to applying that moment. So we're doing the same thing here. Angular momentum, it has it in its name. It's mass times velocity times distance. It's a moment of mass and velocity. And I think that is now kind of sinking in for me, and it might be for you. So if this is first moment of force. This is second moment of area. This is second moment of mass. So now we have right here, we have a moment of inertia. You know what I mean? This is mv. This is a moment of, what would we call it? It's angular momentum. So yeah, just inertia is momentum, and then but yeah. So we have cool. Enough said. But yeah, angular momentum. Oh yeah, the momentum part. I don't know if the word momentum actually comes from like the the Latin, or like the first part of that word momentum comes from the word moment. You know what I mean? Creating a moment. You have some sort of mass that has a velocity, and it's like on a string, like you know what I mean? And so it's a distance away, and so you've just created angular momentum. You know what I mean? I think that probably plays. All right, so let's get back to it. How would we figure this side by summing? Well, we would say, hey, we have a nine force mass there, like this was the mass 9, and then our distance to here is going to be a 3/4 a. And then we're gonna have well, guess what? We're gonna have 2 of those. You know what I mean? Cool. And then check out this. We have 9/4 mass here, and then did we type in the velocity on this? No. You know what I mean? The velocity is gonna be 4 meters per second. Did we put the velocity on this one? I don't think so. What the hell did we even do? We took the distance times the mass. And my bad. No. The velocity is 4 meters per second. So that was just a typo there. So hell yeah. So we have the mass. Well, I should have done the distance first, but here's the r, here's the mass, and then here's the velocity. And there's 2 of these. And then so here's the mass. What should we do next? Well, this is just going to be a divided by 4. That's the r, and then what's the v on the 4 is the v, and there's going to be 2 of them. Cool. So does this equate to the same thing as that? So our a is going to be 1.5 meters. That's what we have. So we have 1.5 divided by 2 times 9 times 4. So this is 27, and I hope I have that right. 1.5 divided by 2 times 9 times 4. Cool. And then so right here, I'm just going to factor out the 9 divided by 4, because we have that in both of them. And then we're going to go 2 times 1.5 times 0.75 plus 1.5, this is the side, divided by 4 times 4 times 2. I totally munched that. 1.5 divided by 4. Oh, how did I mess this up? We'll try it one more time. So we have 2 of these, and they're both 9 divided by 4, that's the mass, times 1.5 times 0.75, and then we're going to add it to, hey, we got 2 of these, times 9 divided by 4, times 4, times 1.5 divided by 4. Oh, bummer. So that did not work. Why the hell didn't that work? That's interesting. Alright, I gotta pause the video. Alright, holy hell, that was brutal. You know what I mean? I was just trying to make a fast video, and then, you know what I mean, we did some sort of error, but I redid it, you know. We have, this is 3/4 a to one of these, and then we have 9/4 for one of these masses, and we have a velocity of 4, and guess what? We got 2 of them. And then plus, these are 1/4 of the, if this is a, we're 1/4 a away, and then 9/4, and then we have velocity of 4 times 2, and so hell yeah. So yep, there's the equation typed in, and we get 27. So that side's done. So now we're going to do the same thing for, so let's get maybe just kind of a fresh sheet of paper. So hell yeah. So we have this side. So we have you know what I mean, angular velocity. We have r cross mv. We did that, and that was 27. You know what I mean? And now we want it to equal this part. And so what the hell does this mean? It means that we have angular, once it hits here, this is like a hinge, and this whole thing is just in pure rotation. You know what I mean? So if we did have this on a hinge, you You know what I mean? It would be there, and then it would be there, and then it would be there, and then it would be there. And then kind of every point in between, you know, it would just be spinning. So we have a spinning square just right around here. Now it's just going to spin for a little bit. All we want to know is the angular velocity once it hits. And because we have the conservation of angular momentum, I'm going to do that same thing. And but we have to do the cross product, you know what I mean? So we have to come here and be like, well, okay, the center of that mass is, but this one's a little bit different. You know how we had these masses were going this way, and then if we took this as our radius, it was only this component because of the cross product. But now we're going to say, hey, this is purely rotational. So if we take a radius to any of these center of masses, guess what? The velocity is tangential at all these points. So we have velocity tangential there, and then we have a velocity tangential, and then take the radius here, velocity tangential, and sweet. So we can still, so our equation is still, you know, we're still doing the angular conservation of angular momentum. We still have that distance, so we have to go, hey, the radius to one of the masses times its velocity. So we go radius to one of the masses, but what the hell is the velocity? Velocity is going to be, this velocity t is going to be the angular velocity times the radius. Oh, so you're going to have two radiuses again. So you're going to have omega r, and check it out, you're going to have m omega r squared. And this is why you get this mr squared term and omega. And guess what? They're going to call that I omega. This is your moment of inertia part. But it's just kind of fun to do it, you know, just with 3 chunks and see how that comes out in the wash. So, and then we don't know omega yet. So we're going to say, hey, the mass, so the distance to this first one, and now we have to get like kind of a check on reality. If this is A and this is A, well, hell yeah, this is going to be, this full distance right there is the square root of 2a. And then this distance to these is, well, this distance is pretty close to the square root of 2 divided by 2. But hell yeah, we got square root of 2a. What you do for this one is you say that this is 3/4 a, and then this is a distance over of 1/4 a. So we're going to take 1/4 a squared plus 3/4 a squared, square root that, and let's just type this in. A is 1.5. 1.5 stored as alpha a. So we got 0.25 alpha a squared plus 0.75 alpha a squared, square root of that. So right here, this distance, I already have it stored as x, so we know that radius. Now this radius is going to be, well, it's the square root of 2 to get to there, but it's going to be 3/4 that. So this one's going to be 3/4 the square root of 2. This one's the same as that x one we just found. And this one will be the square root of 2a, but we just have 1/4 of that distance. So we're just going to divide by 4. So sweet. So now we know our distances to these points, and let's do the first one. So this one's going to be the square root of 2a divided by 4. And I can just do that for you. Square root of 2a, square root of 2 times a divided by 4. Just so you know. So this distance is going to be 0.53. Both of those distances are going to be 1.18. And then this one is going to be square root of 2 alpha a times 0.75. And so this distance is going to be, I don't think I did that right, square root of 2 times alpha a, and then times 0.75. Yeah, there we go. This one's 0.59. All right, booyah. So we have all those, and let's do some plugging and chugging. So here's our radius. I mean, obviously this is going to be radius squared mw. So let's do it in that order. So we're going to find the radius. We're going to square it. The mass is 9 divided by 4. And that's it, and we don't know the omega. So now we have to add, let's do these other two. So we're going to go those distances, and again, this one's going to be 0.53, and then just for a normal number. These distances are going to be that 0.189, and it's the square root of 2a. This one's just in our calculator. Hell yeah, that's just in our calculator. We already did that. We already did this. This distance is for these two. So we have x in our calculator. We're going to square it times the mass, 9 divided by 4, and then omega. So this omega is the only thing we don't know, and then so we'll have to divide that out at the end. But now we're going to have to add this next one. So the radius to this one, what do we say? Square root of 2a, and then 3/4 that. But again, this is just 1.59, and then we're going to square that, 9 divided by 4, and then omega. Cool, and so that's going to equal 27. So we're going to factor out this omega out of this, and then divide all this stuff by 27. So our omega is going to be 27 divided by, and now I'm just going to say 0.53 squared, 9 divided by 4. And you want to get tricky, because we can factor out the 9/4 out of all this. The only thing that I messed up was that we got 2 of these squares. You know what I mean? So let's factor out a 9 divided by 4. And now we just have the distances squared. So we got 0.53 squared plus 1.19 squared plus 1.59 alpha a, or the square root of 2 alpha a times 0.75. 0.75 square root of 2 alpha a. Yeah, so that's 0.59 squared. So hell yeah. So let's just do this in our calculator. And we got 27 divided by 9 divided by 4. Alright, so, and then 0.53 squared plus 1.19 squared plus 1.59 squared. And booyah. And we get an omega of 2.84 radians per second. Now, we're off, you know what I mean? So, that's a bummer. And so why did they get 2 radians per second? Well, we're just taking 4 chunks. And then here's kind of another thing to keep in mind. Let's see. Is that, so if this side was 27, and then we factored out an omega, and then we had all that stuff times omega, and our omega had to be 2.84 to make that equal to 27. So what we're saying is that actually all this stuff is much bigger. And why is that? Well, it's because this radius to right there, we're going to square it. And this isn't, this isn't the effective, oh yeah, so when this thing rotates around this point, hey, like this point is not moving, but this point is like moving hella, and so, and the equation for angular acceleration, or conservation of angular momentum, says that it's your mass, it's your distance to your mass, and then times that mass times the velocity of that mass. Well, in our case, the velocity is omega r, and so if we don't accurately, so this mass up here is going to have it's going to generate way more of this angular momentum than yeah. So it's just you have to cut it into more chunks, and you kind of have to guess that this radius isn't in the center and it's out here, because of this r squared. And let's say this is just a huge area where You know what I mean? It is the difference between saying, hey, this is like 10 squared compared to, oh, damn it. Now I'm just saying words. Yep. Okay, so what I'm going to try to do is finish with if I just did this, instead of cutting this thing into 4 squares, what I want to know is where the effective, this effective kind of center of mass is. If I said I have basically a 9 kilogram mass coming in and hitting this and going into a pure rotation, and what I want to do is just turn this whole problem into a string with a point mass like right there. And so we're gonna, I don't have any more paper, but we're gonna finish with that. And this is brutal, you know what I mean? I think angular momentum is probably one of the harder things, and but I think we'll get something concrete out of this. So we're gonna say, hell yeah, that mass, or that R cross mv on that left side has to equal, well, we have the, we already said it's I omega, but we figure what the hell that was. That was mr squared omega. So that was at least cool. That was probably the take-home point. It's just like, oh, yeah, it kind of spelled itself out once we figured how to take the radius to the mass and then times its velocity. You know what I mean? That's the definition of angular momentum. It's a cross product of pick your point where, cool. So let's do that and call it a video. So this side is going to be 27. We don't have to do that again. And we're going to say, hey, the whole mass of the whole square, that's going to be 9. And then radius squared is the radius that we don't know, this effective radius. But we do know, we're just going to take it from the problem. We're going to say we do know it's 2 radians per second. So now we're just going to solve for r. So we're going to go 27 divided by 2 times 9, and then square root that. So that's r, and we'll finish up. 27 divided by 2 times 9. And so we have radius is 1.22. And then so let's figure out, this side was 1.5, and it's 1.5 meters for the box or whatever. So we're gonna, and then this whole distance from here to there is the square root of 2, 1.4 times 1.5. And so we have this distance there of 2.12, and if we half that divided by 2, the center is at 1.06. So we're not too far off, you know what I mean? We're saying the effective center for this mass is at a distance from this rotation of 1.22. You know what I mean? So and what's that? So we're going to go 1.06 plus 1.22 divided by 1.06 times 100. This is kind of see like what the percent error just by guessing in the middle is. So we're going to take that plus that divided by that. Whoa. My bad. We're going to take, times alpha A divided by 2. So we're going to take this plus this divided by the 1. Oh, I guess we gotta add those together. Divided by 1.06 times 100%. And what the hell? 1.06 plus 1.22 divided by 1.06 times 100. Oh, is that off by that much? No, wait. 1.06. Oh, it's minus. I apologize. I don't even know how to do that equation. 1.06 minus 1.22. And it's just the absolute value. So 1.22 minus 1.06 divided by 1.06. And then multiplied by 100%. Alright, so you got a 15% error guessing that this is in the middle. So if we wanted to, we could go back and then increase these by 15%. So we're going to go and see if that changes things. So we're going to go 27 divided by 9 divided by 4. And then we're going to go 0.53 times 1.15. We have to square that whole thing. Squared. And then we're going to go plus 1.19 times 1.15 squared plus 1.59 times 1.15 squared. And hell yeah, so we get pretty close. We get closer. We get an radians of 2.14 radians per second. So hell yeah. And I'm gonna post this. You know, I mean, it's brutal as hell. But we did it. We did a video on angular. It's even just hard to say the literature words. You know what I mean? We did a problem on conservation of angular momentum. Hell yeah. And it's one of the first, but I mean, if you can't even say the words, you know what I mean, that's a good place to start. And then I'm gonna let's do more of this. You know what I mean? That's why I wanted to do it, but damn, is it brutal. You know what I mean? Just because you have that term that everything is just hidden in this second moment of mass, the mass moment of inertia, or just moment of inertia. That's what it's called, moment of inertia, when you're working with conservation of angular momentum problems. All right, hell yeah. So yeah, we'll do more and we'll get better.